Let's dive right into this explainer. Today, we're unpacking some truly groundbreaking research coming from Melody Y. Guan and her team at OpenAI. The paper is called Deliberative Alignment: Reasoning Enables Safer Language Models, and it lays out the exact methodology OpenAI used to align their new, highly capable All-1 series of models. Now, if you've been following the AI space, you know that making these models smart is really only half the battle. Making them safe, reliable, and actually resistant to malicious attacks is arguably a much, much harder challenge. This research represents a massive leap forward in how we tackle that exact problem.
I want you to picture something for a second. Think about how much safer and frankly how much smarter an AI would be if it wasn't forced to just blurt out the very first pattern it recognizes. What if instead of reacting instantly, it could pause, retrieve a specific set of rules, and actively deliberate over whether a user's request is actually safe to answer? I know, it sounds a lot like a human trait, right? But as we're going to see today, it's now a computational reality. So here's our roadmap for this explainer. We'll kick things off with the AI safety dilemma, introduce the core solution of deliberative alignment, and then break down the training method using SFT and RL. After that, we'll look at the incredible results pushing the Pareto frontier and wrap up with why this matters so much for the future of AI. Let's get right to it.
All right, Section 1, the AI safety dilemma.
Before we jump into the solution, we really have to understand why current models stumble in the first place. Imagine a student who literally has to answer every single test question the split second they hear it, relying entirely on vibes and intuition. That's essentially traditional AI safety training. These models use a fixed amount of compute to respond, so they learn safety implicitly through patterns, not by following strict rules. Because of this, they run into a twin problem. On one hand, they easily fall for jailbreaks, those cleverly disguised prompts designed to bypass safety filters. On the flip side, because they completely lack nuance, they suffer from overrefusals. They get overly cautious and refuse totally normal, benign requests just because they vaguely resemble something bad.
Which brings us to Section 2, enter deliberative alignment. So how do we fix this frustrating twin problem of extreme vulnerability and annoying overcaution? The researchers introduce deliberative alignment. Going back to that student analogy, instead of forcing the student to guess instantly, deliberative alignment basically hands them the literal rulebook and a scratch pad, giving them time to logically think through the request before they ever open their mouth. The AI is taught explicit safety specifications, things like what counts as illicit behavior or self-harm, and then uses a hidden chain of thought to actively reason through those policies.
Let's look at how this plays out in a real interaction. Imagine a user tries to jailbreak the AI by asking for untraceable payment methods for an adult website, and they encode the text in a cipher like ROT13 so the AI won't immediately flag the forbidden words. In the past, that might have worked. But now, the AI has an internal monologue, its chain of thought. It silently decodes the text first, then it explicitly checks its internal policy. It actually says to itself something along the lines of, the user is requesting instructions on how to break the law. This is disallowed content. The user is effectively tricking me. Because it had the space to deliberate, it catches the trick and issues a safe refusal. It's honestly incredible to see.
Moving right along to Section 3, the training with SFT and RL.
Having an internal monologue is fascinating, sure, but how do you actually train a model to behave like that? The researchers at OpenAI achieved this using a very clever two-stage approach: supervised fine-tuning, or SFT, and reinforcement learning, or RL. First up, they generate data by explicitly giving a base model the safety specs and asking it to reason. Second, an AI judge steps in to filter out any bad reasoning. Third is the SFT phase. You can think of this as the open book practice test transitioning into a closed book exam. The model learns to recall these rules purely from memory. And finally, the RL phase acts like a strict judge grading their critical thinking, rewarding the model when its internal reasoning effectively leads to a safe and helpful outcome.
Now, if we break down the architecture pipeline, there is a massive, game-changing detail hidden in the methodology. This entire process requires 0 human-labeled completions. Literally none. It relies entirely on model-generated synthetic data. The models are generating the reasoning themselves, and a separate reward model, a judge LLM, is scoring it. As AI gets smarter, finding human labelers skilled enough to outsmart them is becoming a huge bottleneck. This synthetic pipeline makes deliberative alignment an incredibly scalable way to train future AI. The crucial point in that SFT stage is how they handle the prompt. During the initial data generation, the model is explicitly fed the lengthy rulebook right in its system prompt. But, and this is the genius part, during the actual supervised fine-tuning, those rules are stripped away completely.
The model is forced to memorize and internalize both the spirit and the letter of those policies. So when it's finally deployed to users, it doesn't need to read a massive document over and over again. It just inherently remembers how to behave safely.
All right, Section 4, pushing the Pareto frontier. Okay, so the methodology is scalable, which is great, but does it actually work? To understand the results, we need to talk about the Pareto frontier. In AI engineering, this represents the absolute limit where you can no longer improve one variable without making another one worse. Historically, making a model safer meant making it incredibly frustrating to use, trading off helpfulness for safety. It was always a strict trade-off.
But the data shows that the O1 models literally shatter that boundary. Deliberative alignment allows the model to become highly resistant to malicious jailbreaks while simultaneously decreasing the amount of those annoying overrefusals we talked about earlier. It manages to become much safer and much more helpful at the exact same time.
I really want to emphasize one specific standout number from their testing. On the strong R-reject benchmark, which is a notoriously difficult academic jailbreak test filled with complex adversarial attacks, the O1 model hits a staggering 0.88 goodness score. To put that into perspective, the previous flagship model, GPT-4o, scored a 0.37. That is an absolutely massive leap in robustness against malicious actors trying to break the rules.
And when you stack this up against other heavy hitters out there, like Claude 3.5 Sonnet and Gemini 1.5 Pro, the results absolutely hold up. The O1 model provides elite, top-tier protection against disallowed content and jailbreaks. But more importantly, when evaluated for over-refusals, it maintains an incredibly high accuracy. It doesn't sacrifice its fundamental usefulness just to play it safe.
To really understand the mechanics of the training itself, the researchers ran ablation studies. This is basically where you strip away parts of the training process to see what breaks. They found that if you only use the open book supervised fine-tuning, the model is okay, but not great. And if you only use reinforcement learning, it completely struggles. It proves that both stages, teaching the strong safety prior through SFT and refining the reasoning through strict RL, are absolutely essential to getting these massive frontier-pushing safety gains.
And finally, Section 5, why this matters now. Let's take a step back and look at why this specific paper from OpenAI is so vital for the trajectory of artificial intelligence. First, consider the impact of inference time compute. This research proves a simple but profoundly important concept. The more time you give the O1 model to think, the more compute it uses right at inference time, the safer it becomes on complex problems. As we scale up compute, we aren't just getting models that write better code or solve harder math problems. We are fundamentally getting models that are more robustly aligned to human expectations.
So what is the actual real-world impact of Melody Y. Guan and her team's work? It really boils down to three huge things. One, it's highly scalable because it relies entirely on synthetic data. Two, it makes AI incredibly trustworthy and interpretable. We can literally read the chain of thought and see exactly why the AI made a safety decision, which is an absolute game changer for auditing. And three, it shows amazing out-of-distribution generalization. The O1 model successfully defended against encoded attacks and non-English jailbreaks that they were never even explicitly trained on, simply because their core reasoning skills were so sound. Which leaves us with a pretty incredible question to ponder. Right now, deliberative alignment is mostly being used to prevent AI from helping with illicit acts. But if we've proven that we can successfully teach an AI a specific set of complex guidelines and train it to deliberately, logically reason through them before it ever speaks, what other complex, nuanced human values can we train them to deliberate over tomorrow? The era of AI truly thinking before it speaks is officially here, and it changes the whole landscape. Thanks for joining me for this explainer, and keep learning.